Hello, everybody. Today is our third lesson in the series IQmol+Q-Chem, and I will be showing some chemical reactions. In my series of lessons, the first time I show really some chemical reactions. So this would be demonstration of capability of IQmol and Q-Chem together are to calculate the chemical reactions component, which include reaction, product, and transition state. Let me just share the screen and show schematically what I'm going to calculate. So I will be calculating the series of reactions shown above, where hydrogen connected to carbon. It formed double bond and oxygen. And there's three series with XH group, where X is oxygen, NH and CH2. And this is the reactions which I will be calculating. So formic acid, its transformation to itself by hydrogen transfer from one oxygen to another through the transition state shown here. Then formamide, which transformed to formamidic acid, unstable isomer, and also acetaldehyde is transforming to unsaturated alcohol, ethanol. So, this is schematically shown the reaction path from initial state to the final stage, and schematically shown a transition state. It's a saddle point, minimum energy saddle point, where all vibrations are positive, except one. One is imaginary frequency, which correspond to the path from reaction to product. So this energy, delta E shown, it's energy required to reach the transition point, and delta H is energy outcome of reaction. If delta H is positive, so the reactions endothermic, as in our case. If this point lay below the initial product, reaction is exothermic and the heat is released. So in our case, all of these three calculations, they're more stable isomer transformed to less stable isomer, except as I mentioned, the first reaction, which is just another form of formic acid. So here's energy I calculated. I'll tell you about the method I used. So it's B3-LIP 6 plus G1 star. So, and this energy of transition state in this series is going higher. And this is the heat of formation. So 0 obviously for first reaction, and very similar for the other two. In fact, this transition values are very high for internal hydrogen transfer. So in solution for this, all these substances, this type of transformation actually occur through the high proton transfer from water. Okay, so let's now go to IQmol. Okay, so what I initially show you just how I build this molecule, what I did the calculation, just on one example, and then I'll show you all the results. I already did this calculation because otherwise it will take a lot of time to build all of this to show how you do it. So I'll do it just on one example. So let's, for example, build the initial formic acid. So we select carbon, then we select hydrogen, form carbon-hydrogen bond, then we select oxygen, okay, and then form the double bond, moving it backwards, form another oxygen-carbon bond, and then again I add one more hydrogen connected to this. And at this for this reaction I need the cis form. So that's why so it could be cis or transform. So I need the cis form because this is the one which will be transforming by hydrogen transfer. Okay, so as usual, so we'll do some energy optimization, and here's a molecule. So for all of these molecules in the series, so I did the calculation by optimizing their geometry, and then calculation frequency. and for initial product. So in order to form other molecules, so I would change here their oxygen by nitrogen, adding another hydrogen, and then by carbon, adding 2 more hydrogens. So most interesting, of course, is transition state calculation. So in order to start from a right structure, in this case, it's easy to expect that hydrogen will be somewhere in the middle between duo, because it's kind of symmetric reaction. So it's easy to expect the hydrogen would be in the middle. So I did the following trick. What I did in order to, so I kind of tricked there, in a sense, the program. So I turn this hydrogen into oxygen, form this bond. Okay, and then, so I would need them to be equal. So in this case, what I do, I remove this double bond, form a single bond. Oh, sorry, no, just a second, that's not what I want. Display, select none. So I need to form a single bond. So I clicked on oxygen again. Form single bond here. Okay, so the carbon I still want to be double bonded. In this case, I'm tricking a little bit the program, see if it works. Let me see this. No, I don't. Oops, I turned to carbon. Okay, so sorry, I need to turn it into carbon back. No, it's bicarbon. So I want to form this double bond. Obviously, it's a trick. So there is no double bond with hydrogen, but I want the structure to be symmetric. So I optimize it. Okay, so it's becoming a C2V structure with equal bonds. So I can actually make it symmetric, symmetrized molecules. It shows that it's become C2V, which means equal bond between oxygens in planar structure. Let me move it in the middle. Okay, so, all right. Okay, so now what I do, I turn this oxygen back to hydrogen and use this structure as initial guess for searching the transition state. And it actually worked. So for quantum chemistry calculation, this formal bond definition doesn't matter. So this bond would be equal anywhere. So it can showed by double bond, but if you don't like it, then you can change it back to single bond. So now I go to calculation. I do the Q-Chem setup, and I mentioned, so I select as a level, I select B3 leap, and 631 plus G star as a basis set. So I need to do geometry first. No, not geometry. In this case, a transition state. I go to search for transition state. In other cases, if it's molecule, then it should be our geometry search. So in this case, a transition state. It's a job one. In order for me to understand that I get the right structure and with the right transition state, I need to do another calculation. I submit there. I add another job here in green plus. So the second job will be frequencies. So and now I can submit the job. So I have to give it the name. Okay, as I mentioned, I did all this calculation. So just a demonstration for you, I click on OK, and it's went. So I will not save the result here because, as I mentioned, I have it when its calculation is done. So I'll simply mention that I don't need it. So, okay. However, for me to show you the transition states here, I'm going to the transition state, and that's how it's look like. This is a transition state which I have calculated. So let me just show you in a more right position. So this is a transition state. In order to be sure that the transition state, I need to look on the frequencies. So I will go to the frequency and see this is the imaginary frequency. It's called I imaginary, and this is and now I can show you, if I double click on it, you see that hydrogen is moving from one oxygen R to another one. So, and all other frequencies are positive. So that means I found the right transition state here. Okay. All right. So what I did then, okay, good enough. How to stop it? Okay. So I did repeat the same calculations. Okay, now let me show you again. So what I did next, in order to find the transition state for transform from formamide to formamidic acid, so I replace this oxygen by NH group, and then started the transition state calculation again. And I'll show you what I get in this case. The calculation finished, results are from service. No, I don't need it because, as I mentioned, I already did the calculation. So let me show you another transition state here, which I got. You see, it's quite similar by its structure. Let me just show you that it is a transition state that we need. Again, I go click on frequency. You see that's imaginary frequency. And it's again, it's a right moment between oxygen and nitrogen. Okay, so good enough. So it's always again doesn't want. Oh, this is the frequency. When I double clicked, it showed the spectrum actually. Okay, so next, the last one, transition state. It was kind of more tricky to get because if I change here nitrogen by CH2 group, so the transition state cannot be any more planar. So, and I needed to trick a little bit, rotate the CH2 group, and it's actually I needed to do it a couple of times because the direct calculation of a transition state of this kind not always easy to calculate. However, I finally succeeded, and I show you what it is. Okay, so I need to show you the structure first. Here, oops. Oh, it's actually I showed you the bonds here, which I want to show you later on. So let me just remove it. Oh, I showed them an orbital. I don't want to see the orbital, guys. Let me see the frequency. Okay, so somehow, oh, okay, so it's show because I showed you the orbital features. Okay, so here's the transition state for oxygen, for hydrogen transfer between CH3 group in acetaldehyde to oxygen to transform this here, the double bond, and the ethanol. So again, so as you may see, the calculation I did is correct. So the structure is actually clearly shown that it's right. You see, this structure is not that well. It's kind of in a plane, but it's a little bit tricky to get because you need to rotate CH2 a little bit, and you don't know exactly the angle, and it may actually fall into some other transition state. In case if you want to get these tricky structures and you cannot get it, so you can contact me at my email address, corkin@nanoandgiga.com, and I'll send you the structure, and maybe we can just practice together if you're interested. I'm actually open for communication directly with students and people who are interested in my lesson. Okay, so let me double click. You see, same as in the previous transition state, but it actually slightly rotate around the carbon-carbon bond. So that's the last transition state. Okay, all right. For some reason it's always okay. So now it's stopped. So in the same way, I found all the structures, initials, final, and the transition state. And how do I calculate the barrier? So what I do, if you go to one of these molecules, or initial one, so you go to geometries and look in the very last energy, and this is the energy of the molecule. And for all the same structure, initial, final, and transition state, I look for this final energy and calculate the difference between the initial molecule, final molecule, and transition state. This energy is given in Hartree, and Hartree is transformed into kilocalorie per mole by the factor 627.5. So when you calculate the difference between these numbers shown here, you have to multiply it by 627 pi, and then you will get the energy difference between structure in kilocalories per mole. What is also interesting is to take a look on some of the molecular orbitals. Usually, when we analyze their reactivity of the molecules, we normally look at their highest occupied and lowest unoccupied orbital. The highest occupied orbital with 2 electrons show you how the reaction may occur with electrophilic with electrophiles, while lowest unoccupied orbital is will show how it will react with nucleophiles. So if we go in the surfaces here, for example, for these molecules, and you look on canonical orbital, to calculate it, you need to double click on canonical orbital. So I clicked on calculate, but I already did it. So, and I calculated the highest occupied and lowest unoccupied. So if I click here, it will show up. So you can see for formic acid, the highest energy occupied is in plane, and in the area of interesting for us, it's kind of non-bonding. So it's actually a combination of lone pair of oxygen. Here it's transferred to hydrogen area on carbon, and lone pair on other oxygen. So that's how the highest occupied orbital looks like. So highest non-occupied is, in our case, is has a pi bonding character. So, and it's you can see it's non-bonding orbital. A major part of it's on carbon, but it's actually distributed between both oxygen. Despite this, it's a double bond. So the lowest unoccupied orbital is kind of more or less symmetric between sharing part of it between other between both oxygen. So in the same way, we can look on all other orbitals. Yeah, for interest, let's, for example, take a look on the orbital of a transition state. Okay, this is a transition state, and now, for example, I want to take a look and the orbitals highest occupied for the transition state. So again, same as for initial molecules, it's in the plane, it's somewhat form, it has non-bonding character in the transfer, in the area of hydrogen transfer. It's kind of mostly non-pair orbital of oxygen. In non-bonding orbital is also pi orbital. It's pi orbital, and it is bonding in the area of hydrogen transfer, and it's mostly again on carbons. It's kind of similar to what we had for the initial molecule. So in the same way, you can take a look on all orbitals in structures and everything for all of the series. So you may try to repeat this calculation. It is quite an interesting exercise. So that's all I want to show you for today. So thank you very much for your attention.